Hello, and welcome to our second module of Plant Diversity, Climate Change, and Conservation, the View from California. And in this module, we're actually going to step back and I'm going to give you a very fundamental introduction to what drives global climate, and that'll set up our discussion of vegetation and climate change as we go forward. So quite different from our first module, thinking about all the factors driving the complexity of historical change. Now we're going to go into some very basic physical factors that drive how climate is shaped on the Earth, and use that as the context for understanding California. And some of you may be very familiar with aspects of all of what I'll share today. At a global level, I would say the three most important drivers of global climate are the latitude, how far are you from the equator, elevation, how high are you in the mountains, and where are you relative to continents and oceans? And we'll look at that in a moment as we go forward. Latitude and elevation. Latitude has a very simple physical effect, and it is literally, it's just the geometry of how the sun hits the Earth. So if you look on the left, where that yellow, each of those yellow bands would be a band of sunlight coming down and hitting the Earth. When the sun hits at the equator, it hits straight on. It just hits at a right angle, and that means the sun is stronger. And if you spend time even in Southern California, certainly if you spend time in equatorial latitudes, you know that feeling when the sun is straight overhead and beating down on your head. And as you go to higher latitudes, and either in the Southern Hemisphere or the Northern Hemisphere, that same amount of sun is just laid out at an angle over a larger amount of land or ocean, and that just leads to cooler temperatures. And this is all captured in something called the cosine of incidence equation, for those who want to look at some of the math behind it, but a very simple equation. So it's warmer closer to the equator, a pattern we're all familiar with, and that is driven by the geometry. The elevation, the physics is totally different. That air is stacked up in a big column over our head, wherever we sit on the Earth. And even though air feels weightless, it does have mass and pressure and all those molecules, and the molecules press down on each other. So the pressure is higher at lower elevation. And then it gets lower as we go up. And of course, part of that lower pressure is that there's fewer molecules per unit volume of air, and that's why you have trouble breathing when you get, most people by the time they get to 10,000 feet, if not before, are really noticing that the oxygen pressures are lower, and it is harder to breathe. It helps if you adjust over time. But when molecules bump into each other, the temperature is, in a sense, what happens when molecules bump into each other. And as there's a lower density of molecules, they're bumping into each other less often. That's going to be the biologist's explanation of the physics, because I'm not a physicist. But of course, that drives lower temperatures as we go up in elevation. So we look at a global temperature map, and those two factors, together with the oceans, in a lot of detail, of course, and there's a whole lot of ocean circulation involved in this we won't go into, but it gives us the main pattern. It's hotter across the tropics, all that red across all three continents. Six continents. We're not looking at Antarctica, which is off the map there, but all that red right across the tropics. The three major tropical regions of the world is what I was trying to say. The neotropics, all of Africa, the Indian subcontinent, and then Southeast Asia. You see all that red. Okay, it gets cooler towards the north, the blue, the very cool temperatures high up. But then you look in detail and you pick up the elevation. Look at the Andes, the cooler temperatures in the high mountains. You can just pick up the Sierra Nevada. And then one of the most dramatic is from the very hot temperatures of India, and then the Himalaya just rise up, and it just goes from red all the way down to those light blues, and then the Tibetan Plateau, which sits at a very, very high elevation. The other factors we won't go into, we'll talk a little bit more later in a California context, have to do with the way the wind blows and the influences of the ocean come across the continents, and just the shape of the continents. The shape of the continents matters a lot. So bring that into California, and we see, of course, warmer in the south, cooler in the north, and we see the cool high mountains. In Sierra Nevada, we see the coast ranges, and especially the Mendocino, Klamath mountains, the Cascades. And then what we'll come back to and talk about is the ocean effect along the coast. Now, for rainfall, latitude has quite a different effect. And I can tell you, having taught several rounds of introductory biology, that I don't think I have ever fully succeeded in teaching this in ways that my students have found fully satisfactory. But this is the global air circulation patterns that come from effects of latitude and the spinning of the Earth together have a major effect on rainfall patterns. In brief, as the sun beats down at the equator, it evaporates a lot of water. That water rises in the atmosphere. As it rises, it condenses. As it condenses, it rains. So the moisture is both driven off the surface of the Earth and it rains right back down, and that leads to the very, very high rainfall in the tropics. After having lost all that water in rainfall, the air is being lifted up by the high temperatures of the tropics, loses the water, and it hits, as it approaches the top of the atmosphere, it has to go somewhere, and it splits and goes both directions, both north and south. And this is called the Hadley cell. It goes for a ways, gets very, very, it's dried out, it begins to descend. As it descends, it sucks the moisture into the air. It's the opposite effect. It gets drier and drier. This actually, we'll come back to this in relation to fires in California, I think, and comes down as very dry air and leads to a zone of the deserts. And then actually the whole thing is repeated a couple more times going up towards the poles. Okay, so we have these circulation patterns. We also have the Coriolis effect from the spinning of the Earth, and we'll set that one aside for the moment, but that really sets up the prevailing winds as well. The effect of elevation on rainfall. Again, it's, elevation affects temperature, it affects rainfall for a different reason. So if we have air, especially when air comes off the ocean, moving across the land, as air masses are pushed up over the mountains, they cool, and as they cool, the moisture in them goes from being in vapor state to liquid water, and we generate rain. This is called an orographic effect, where orographic refers to an effect of mountain ranges. So this is illustration. This is a textbook illustration, but it might as well be California with a little bit of the coast range missing. So the water comes off the ocean, crosses the Central Valley, heads up the slope of the Sierra. You get this very high rainfall, and this is the very productive conifer forest range up over the mountains. As it goes down the other side, there's actually two different things that happen. First, there's just less water left because all the water came out here in the rain. Also, the physics reverses. So just as rising air makes the water condense, descending air makes the water it gets pulled back into the atmosphere. So it's even further from condensing. So the air gets drier and drier and drier. So the combination is you lead to rain shadows. So the opposite side of the mountains behind where the winds are coming from become very significant rain shadows. So let's look at a global scale. Wet right across the equator, and then you have the Hadley cell setting up, and you get dry in the desert band. The continental geography moves that a little bit in the mountains, like the Himalaya push that up, and you get the Tibetan Plateau, Central Asian deserts, but certainly right here, that's right at the descending arm of the Hadley cell. And then here's the other descending arm of the Hadley cell in the southern hemisphere, northern Chile, the western Cape of South Africa, the great outback desert of Australia. But then we add to that mountains. So for example, here we have mountains that capture all that moisture. So once you get past that desert zone, you can see the complexity that comes from all the mountains. So different from, say, from the Sahara, even at roughly similar latitudes. So we see elevation, we see mountains, we see rain shadows. Zoom into California. The Southern California is approaching the edge of that, the northern edge of the desert zone where the Hadley cell descends. So of course we have very, very dry deserts, the edge of the Sonoran and the Mojave Desert. Then we have orographic effects that pick up water off the ocean and lead to high rainfall in the Coast Range. And we have a rain shadow. So certainly when you drive I-5, you know how dry that side of the Coast Range is when you're sitting right in the rain shadow of the Coast Ranges, and how dry the San Joaquin especially is. But then the air gets across the Central Valley, starts rising again, rising even higher, and we have all the rainfall that falls in the Sierra Nevada, and then another rain shadow, and all of the Great Basin sits in the rain shadow of the Sierra Nevada. So this gives us our major precipitation patterns. Now layer on the geometry of the Earth going around the sun, and the fact that the Earth has a little tilt. Both of these things are important. So with that little tilt of the axis, it means that the northern hemisphere is pointing towards the sun part of the year. That becomes our summer because it's warmer. The northern hemisphere is pointing away from the sun, even as the Earth spins. And of course, that becomes our winter. And then we have the spring and fall equinoxes as well. In addition, the what are called the Milankovitch cycles, the shape of the orbit and the tilt of the Earth have changed over time. And as that shape of the orbit changes and the tilt changes, the intensity of the summer-winter swing has changed. And that actually has been a major driver of the ice ages. Okay, so there's some basic physics. Now let's pause and look at going back to Earth history, look at the history of temperature on planet Earth. Now, I love this figure. It takes a moment to read though, because what they've done, and this actually, you see the source below, is the timescales change. Let's go from this side. First, it's just 20,000 years. Okay, so that's the timescale of the right-hand panel. Then it goes from 20,000 to a million. So now we jump into hundreds of thousands of years. Then it goes from a million to about 7 million, then 7 million all the way to about 70 million, and then 70 million to 500 million, half a billion years. So the timescales are compressing as we go to the left. We'll skip that first part, but go here, because this is really where the sort of the modern temperate world emerges. And I'm not going to go into all the causes of why all this happened, right? This is the extinction of the dinosaurs at the KT boundary. We actually go up to the temperature's warm. There's a couple of interesting spikes in there, and there's some very interesting fossil evidence of what happens in those rapid spikes. But we have this Eocene maximum. That was the warmest the Earth has been in the last 100 million years, and this is at about 50. Things go down, and also the world starts getting drier in general. The temperate zone emerges. The world is mostly tropical at 100 million years ago because it's so warm. As it cools, the temperate zone really emerges, and a lot of modern plant lineages actually evolve out of the tropics into this emerging temperate zone. And it's not necessarily that they move. It's funny, we think of plants moving from one zone to another. You have to think of it the other way. The plants might have just been sitting there, but the climate went from being tropical to temperate, so they evolve and become temperate plants because the climate is changing, literally we'd say under their feet, but let's say under their roots as they sit right there. So a lot of biogeography going on through this period. Then we get into the Pliocene, 5 million to 1 million years ago. The evidence suggests that this is when the Mediterranean climate emerges. We'll talk about that later. And then we get into the Pleistocene with the ice ages. And these ice ages are driven by changes in those Milankovitch cycles, the orbit of the Earth, the shape of the ellipse, the tilt of the Earth, that just drive us back and forth. And this shows us how ice ages tend to take a long time to go in and then come out very fast. Long time in, come out very fast. And that's what we saw in our first unit, where we saw the oaks very quickly spreading just in a few thousand years coming out of the last glacial maximum. Now we come to the last 20,000 years. We're kind of saying some of the same history there. There's that period when pines are replaced by oaks in central California, a little dip, a little warming, and then this very, very stable period. The Holocene has been one of the most stable climatic periods sort of for that duration of time in certainly the last million years or so. This is the entire span in which human civilization takes shape. Major cities take shape. So the location of cities, sea level, the climatic zones, we've been living in a very stable period. And if you've ever seen Al Gore's movie about climate change or others that talk about the hockey puck, I guess that's a very maybe Canadian or Eastern reference to the hockey stick, to go to a hockey stick. But the hockey stick refers to the long handle and the sharp turn on the temperature graph and what's shown here is that against this long period of the Holocene, where we could be headed, we'll talk more about climate change, is to temperatures that are then the highest that we've seen going back to 5 million years ago or so. And that really is what we're facing right now. I was going to use a more detailed slide to tell some of that story, but I've already told it. So let me jump forward. So temperature has this long arc and, long descent and then coming out of the ice ages. Rainfall is quite different when we think about the history of rainfall. Rainfall is, the best way to think about it is it's variable at every time scale. Here is about 100 years of western U.S. rainfall history, and you just see droughts and rainy years and a little wetter at the end of the 19th century. Then you compress that and you look at the last 500 years and you just see rainfall up and down with some major droughts. You can compress that 500 years and then look at 2,000 years and you see long periods of drought followed by sort of average wetter periods. So at every scale you look at rainfall, it's highly variable. And we have every reason to believe that in the future in California, it will continue to be highly variable. That is the most important message. It might be a little wetter on average or a little drier on average, but the more important part is that when these droughts occur, will they be more frequent? Will they last longer? So where temperature is about a general trend towards warming, rainfall is about how variable will it be? How long will the dry periods last? Will it go up and down more? But the variability of rainfall is absolutely characteristic of especially of Western North America and of California. And that wraps up this second unit, setting the template to think about climate and climate change as we move forward.